Recording started.
My name is Marissa Saunders, and I am going to talk today about clustering Clickstream data using Spark. To give you a little bit of background of who I am, I'm a data scientist here at Think Big, and I am excited to be able to give you some insight into this great new technology that we're using and some practical applications of Spark. So, what I'm going to talk to you about today is, first of all, some whys. Why is clustering useful? Why is Spark a good choice for clustering in the big data environment? And why is Clickstream data interesting and useful in a business? Next, I'll tell you a little bit about what is the raw data that we get, what does it look like, and then go into how. How do we turn this raw data into useful information using two steps. First of all, parsing the user agent data to give us better information, and secondly, using a clustering algorithm, distributed K-modes, on Spark. And then I'll give you a little bit of the motivation of why this is a good thing to do, including the details of how you apply the method to this particular use case, taking a quick look at the resulting clusters that come out, and trying to understand how these clusters describe the users and how these different user types access websites in a different way and access both with respect to time and with respect to which sites they access. So in addition to that general outline, there are specific objectives that I want to try to communicate today. The first is a set of things that I'd like to convey some understanding about, and those are: what are K-means and K-modes clustering? Why is Spark a good choice for this? What are the basic data structures in Spark? How are they different, and why are each one of them useful? And then, what is Clickstream data, and how does user agent parsing work? I'll also demonstrate a couple of technical capabilities that are useful in a wide variety of different use cases, including how to map a function over an RDD. That's one of those data structures in Spark. How to define a custom user-defined function and map it over a data frame. That's another data structure in Spark. How you can use generic Python to map a function over an entire partition of data. And I'll get into a little bit more about what a partition is in a few slides. And how you can identify different user types using this algorithm, and how this can drive insight into user behavior. So let's jump right in. Why clustering? Quite frequently, if you have simple, small data, you can plot it and look at a plot like this. It's pretty obvious visually that you have two groups of data. And clustering is useful because if your data is more complex, you can't find them by just looking at a plot. Clustering can help you find them in an automated way. This can lead you to insight. In this case, we're looking at the mass and airspeed velocity of different birds. You can see there are two different types of birds. In this case, they're unladen swallows. That heavier species flies more slowly. And in general, when you're asking for airspeed, we should specify whether we mean African or European swallows. For those of you who are Monty Python fans, I apologize for the liberties. So how does clustering work? In general, it's a very straightforward algorithm. What I will walk you through first is called K-means, and this works well in continuous data. So the way this works, we first pick 2 points from the data at random as our cluster centroids. I've shown those in red with the little arrows to help them pop out a little bit better. We then assign all of the different data points in our data to a cluster based on how close they are to those centroid points. So here you can see we've generated a cyan group and a pink group. We then recalculate the centroids as the mean or average position over all of the data points in a cluster. And you can see now those 2 points have moved quite a bit further apart from one another and are starting to look like they're getting close to the center of the 2 clusters we would pick out by eye. We repeat these steps a few times until we get some level of convergence. The spots or the data points quit switching clusters, and that's the algorithm called K-means clustering. Spark has a built-in function for this in both ML and in MLlib, and it works fantastically. The problem is when we come to categorical data. So categorical data is data that can't be described as a number. here I've given some examples of transforming these continuous variables of mass and speed into categorical variables, such as heavy and light and slow and fast. But I've added another example of something that's not so easy to understand in numerical terms, which is color. So green-gray or green-black. I don't know how to assign a number to that, and so it's really difficult to do anything like k-means. What we do instead is we use modes. Modes are the most frequently occurring value in a group. So if we look here at the top 4 different data points for African swallows, we see that the mode in color is green-gray. There are 3 values that are green-gray and only 1 that's green-black. In this way, we can work with categories and not need to assign numerical values. We also, when we try to calculate a distance between points, need a way to measure the distance. And we use a very simple metric that is 0 if the 2 points are the same and 1 if they're not the same. And then we use the same iterative cluster assignment algorithm where we pick out centroids, calculate the distance using this binary distance metric, update the modes, so figure out what's the most frequent value in each cluster, and repeat this until we get convergence. This is called k-modes clustering, and it didn't have a function for Spark, but we've open sourced one, and I'll show you the link for that in a few slides. So I've mentioned Spark a couple of times already. Why is Spark useful? The definition from Apache is that Spark is a fast and general engine for large-scale data processing. Spark does distributed computing. It relies on an external distributed file system. In our case, we typically use it with Hadoop, so that's HDFS, but it can sit on top of really any distributed file system. The advantages that Spark has, and we'll talk about this in a little bit more detail in the next few slides, is that it works in memory. It has an optimized execution engine, and it has a lot of high-level functionality. It has these libraries like ML and MLlib that already have machine learning algorithms coded, and that helps speed up time to development. So why Spark? Really, I love Spark because it's fast. It's faster to compute. It's faster to develop. So the reason that it's fast is that first it takes computation to the data. This is the general paradigm with MapReduce and with Spark, where you have the data sitting on different worker nodes. You run the program on a driver node, and then when it needs to do something to the data, it ships the program to those nodes, and it performs the computation on the data where it lives so that you avoid communication costs in between the worker node and the driver node. Spark is faster than MapReduce, though, for 2 reasons. First of all, it has this in-memory operation, so it keeps data in memory on the worker nodes, and that avoids the read-write costs associated with MapReduce. The second advantage is that Spark is a lazy executor, so you can tell it to do multiple different operations on your data, and it won't do anything until you finally tell it at the end, calculate and show me these 5 rows. When you then say calculate this, it optimizes which operations need to be done, and in that way reduces computational costs by not doing things that you don't need it to do. As I've mentioned already, Spark is also fast to develop. So because it has these data transformation machine learning libraries already built in as part of the Spark ecosystem, you don't have to spend time writing those algorithms from the ground up, programming them in MapReduce, and that speeds up your time to actually get answers. Let's talk about the basic data structures in Spark. The first and most basic of those is the resiliently distributed data set, or an RDD. The idea with an RDD is you take a full data set, you break it up into pieces, and then you ship those pieces to worker nodes and store them on different worker nodes so that each different node is responsible for a different amount of data. There are a couple of interesting features that you'll see here in the diagram. The first is that you store multiple copies of each block. So we split up the full data set into 8 blocks, but you'll see that block 1 is stored on both this node and this node. This helps to increase the resilience to failure if Spark goes down, because if one of these nodes goes down, the data is already there on another node. The other thing that's done to make this data set resilient is that each node stores the lineage of the data in addition to the data. So what that means is if I have a data set that I've read in from a file, and then I add 3 and multiply it by 5, then when I do that computation and cache it in memory, Spark not only says this is what the resulting data is, it also says to get here, I took this file, I added 3 and multiplied by 5. And so that means if one of the nodes go down or all of the nodes go down, then Spark can get back to the data that you told it to have without throwing an error. The second data structure in Spark is a data frame. And basically this is just an RDD with a schema. This is part of Spark SQL, and it enables you to query your data in a SQL-style syntax. It's very convenient because your data is broken up into a more traditional record-type format, and each column in the data can be queried by name. It also relies on the Tungsten engine, which is part of Spark that optimizes queries. So in a lot of cases, it can be faster than an RDD. And if you're relying on an external storage source like Hive, it actually does a lot of push down into Hive. So it will pass the query into Hive and let Hive's optimized engine do the query before it pulls it into Spark, in that way speeding up queries. The final data structure in Spark is a data set. So it's really pretty early on for data sets. They just came out late last year, and they're not in Python or in Scala yet, but we're hoping that they're going to have the best of both worlds, some of the features of a distributed data set that people have really liked over the years, along with some of the convenience of a data frame. So let's set up a little bit of terminology before we go into the use case itself. I've shown this diagram and talked about the full data set and it being broken into pieces, each sitting on a node. Each of those pieces is called a partition, and each of the entries in that partition I will refer to as a record. So why is Clickstream data interesting? Clickstream data can be thought of as an information trail left behind by each user. Typically, this lives in semi-structured log files on a website, and it includes things like who's browsing, the device, the operating system, and the browser, where you're located, the time zone, latitude, longitude, city, and country, what time the website is accessed, where the user is coming from, and which particular page in a website is accessed. So why is this useful? There's a whole field of web analytics that answers questions like, when do users visit the website? Where are my users? What pages are users visiting the most? Which pages are the most efficient at selling? How do users navigate through my website? Things like this based on Clickstream data. And so there's a lot of really good business insight that can come from this, including how do you optimize the design of a website to promote people finding it easy to use, finding it easy to navigate, and how do you market? You can keep track of what marketing channels drive users to your website, which are productive users, which are high-quality users. So in this case, I'm going to walk through a sample use case. This is an open data source. It's Clickstream data from OneUSA.gov. And basically, OneUSA.gov is anytime a person shortens a U.S. government site, that is .gov or .mil, using bit.ly, it creates a link that ends in OneUSA.gov. There's a streaming feed of everybody accessing these sites at the link here in this slide. And in addition, there's an archive for 2 years' worth of data at this link. I think this is a great data set to experiment with. It's got a relatively large volume in the archive. It's realistic in the sense that you can experiment with what it's like to work with streaming data, and also the typical errors that you'll get in a data stream. And you can answer some really interesting questions like what subtypes of users are looking at these government sites, and how do the activity patterns of these subtypes differ. It's also publicly available, so it's not confidential data, and that means people can experiment with it, try things out, and put to use the example that I'm showing you here. So what does the raw data look like? This is a typical entry in a Clickstream data. It looks pretty messy. It's typically in JSON format, and it will include things like the website that the person clicked on, where they're coming from, if it was a direct click or if they came from some other website. information about the user agent. So this is what we'll be parsing to get a lot of the information we want to use going forward from. And if you parse this, you can actually figure out, is this a PC? What operating system are they using? What browser are they using? And so on. It also will have the time that the user accessed the website, their time zone, so on and so forth. So to get from this data to something useful, we have to do some parsing. And the high-level picture is that you want to take this JSON format entry and pull out things like, what day was this actually? What hour was this? What type of device? Was it a PC? Was it a mobile phone? What browser was it? What was the operating system? And is it a bot, or is this actually a genuine user? The way that we'll do this is we'll write a function for one record in Python, test it in Python, and then once we know it's working, we'll map this function over all of the records in this data set using Spark. So the actual transformation uses this external library called user agents. This is what the parsing function looks like. We import this external library, and then we do some transformation to put the string into the proper encoding, and then we just run the function parse this string. And that will give us back information about the user agent generated from this library. Once we have this Python function working, we then map it over the entire RDD. Oh, there you see. Here is our RDD containing the parsed JSON data. Then we define this lambda function that says for every record, let's take the record, put it into a list format, and then apply this custom function to this particular part of the record, which is the user agent string. So now that we've got the data in a reasonable format, we need to do some clustering. And we want to use K-mode's data, or K-mode's clustering, because this is categorical data. The problem is that when we do clustering, and in this case I'm showing K-means just because it's easier to visualize, when we do clustering, each cluster is a property of the entire data set. So how do we do this in a distributed way? How can we put it across many nodes? The answer is pretty simple. We basically split this randomly into, say, 3 partitions, and then we do our clustering on each partition. From each partition, we'll get some cluster centers, and we then bring all of these cluster centers to the driver node and run one final clustering operation to cluster these centers and get a final center. So we've already talked about how you can map over a record in Spark. We did that when we were doing user agent parsing. What we now need to do is something a little bit different. Rather than mapping over each individual record in a data set, we want to map over an entire block. And there is an equivalent of this in Spark. There are actually 2 different ways you can do this. The one way is just to map over a block of data, and the second is to keep track that this is block 1 and then do something for each record in the data. The way this looks, just as a technical reference, is that if you're mapping over a record, you define a function that takes as its input a record, and you return some transformation on the record. When you map over a partition, you define a function that is a function of an iterator. And an iterator basically is that it's cycling once through each record in that partition. You then get back from that some value calculated over the entire partition. And then you just apply that to an RDD in the same way that you would apply map, only calling map partitions with this function of an iterator instead of a function of a record. Finally, if you want to keep track of that key, then your function has to take 2 inputs. One, the index that tells it which key, which partition you're working on, and 2, the iterator that will go through all the records in that partition. And then you just call map partitions with index, passing in that function in order to get it to call over each partition. If you don't care about those details, then for K-mode, we've open sourced an implementation of distributed clustering that you don't need to worry about any of that, and the link for that is here. So how do we apply this to the OneUSA Gov data? We first have to get the OneUSA Clickstream data. I'm not going to go into the details here, but the basic idea is that we have to scrape the data from the archive site, concatenate the data into one file per month, we load it into HDFS, and then we pull it into Spark. Spark has a JSON reader that makes that very convenient. To read the data, we point it at a file path. I have multiple files in this path, so I'm going to do a little loop over each of those files in that path and just join them all together using a union all function into my sample data RDB, or data frame. This is whenever you see a SQL context, that means you're reading into a data frame. So when we look at this, the great thing about data frames is that it will infer a schema from the JSON file. So it will pull out all of the column names. It will determine what the data type is, whether it's a string, a long, and whether there are null values in there. And it does that with just this simple call. We then take this data and we have to parse it to get the user agent information out. In this case, we had to do a little bit of custom parsing after we called user agents to pull out the fields that we were interested in, the operating system family, operating system version, a device, so on. And then we use Spark to map this function over each Clickstream entry, as I've shown already. We grab the data frame, we map this function over the data frame, and it gives us a parsed RDD in return. There's one more thing that we have to be aware of when we're preparing for K-modes clustering, and that is the curse of dimensionality. So this is a great figure that I found from Prasad Patil, who really visualized what the curse of dimensionality is. So if I have data in one dimension and I split that dimension in half, I'll capture about half of the data. If I have two dimensions and I split each dimension in half, I will only capture about a quarter of the data. And this gets worse and worse. When you go to 3 dimensions, you'll only get about an eighth of the data. When you go to 4 dimensions, you'll only get about a 16th of the data. What that means is whenever we're trying to cluster data, we need to make sure to reduce the dimensions to the bare minimum that we need in order to avoid getting a lot of empty space in each of our clusters. So some of the things that we're going to do to reduce dimensionality is decide which variables we should use for clustering, and keep only the top few categories for each variable. So for example, for time zone, there are 24 different time zones. But if we look at the data itself in this use case, there are only about 3 or 4 that actually have a high number of hits. And so we'll group by those 4 time zones plus another category. The variables we decided to use for clustering were country, time zone, device type, operating system, and browser. And as I said, we'll keep just the top few categories. Here's an example of how we did this. This also provides an example of how you can define a custom function to apply to a data frame. The difference here, we've done mapping over an RDD, but for a data frame, you have to tell it, in addition to what's the data that I want to fill in, what type of data am I giving it? And so you can see the way that this works is we define a function, just like we did in the mapping case, that looks, is the time zone in our top 6? If it is, then keep that value. If not, if there's nothing there, return no geo info, otherwise return other. To define this as a user-defined function, we just tell it the function name and the type of data it will return, and then we can call this UDF function over a data frame just by passing it in and this with column syntax. So we take our original data frame, we say add a new column called new user, apply this function to this existing column, and we do that for a series of different columns to reduce dimensionality in this case. So then we're ready. We can do K-modes clustering. What we've done just from a large-scale view is we've taken the full log, we've partitioned it out to create an RDD that's been parsed. We then want to do distributed clustering and then pull those centroid points together to do a final local clustering step. We're going to use this open source package that we've released. It looks a lot like scikit-learn. Basically, we tell it what type of clustering we want to do. We say we want to do ensemble K-modes. We want 10 clusters out, and we'll do a maximum of 10 iterations to convergence. We then fit this method using our data. This is our input data. And we can pull out our predictions and zip them up with our original input data to get input data and the cluster that has been assigned by our algorithm. And now we can take a look at what we get out. So if we look at the 10 clusters and we try to determine how many data points are in each cluster, we see this distribution. We see there's one cluster with a lot of entries, and the rest of them are more or less level in terms of how many entries they have. None of these are extremely small. They're all between at least 100,000 hits, so that's reasonable. We're not over-clustering. We can also look at what are the properties of these clusters. So if we look at the most frequently occurring value in each category, in each cluster, we can map it out like this. So here we've got cluster 1. It is the largest. It's got about 600,000 hits to the website in this cluster. These are mostly coming from the United States. These are mostly PCs, and these are mostly on Windows 7. We can see the second cluster is people outside the U.S. These people happen to be mobile users on their Apples. There's a third cluster, which is people who've turned off geolocation in their browser, so we don't know where they are. But mostly these are people on a PC using Chrome or Internet Explorer in Windows, and so on. We can additionally say, okay, so we understand there are these different clusters. Do they use the website differently? One of the things we can look at is what time did they access the website? So here we've taken each cluster. We've looked at how many hits they get for each hour of the day, and this time is adjusted based on time zone. So if they're in Central Time, they'll be normalized to Standard Time before we plot this out so that this is 10 o'clock local time. And what we see is for the people in the U.S. who use Windows 7 on their PCs, they mostly access U.S. government websites during the week between about 8 and 5. There seems to be a peak on Tuesdays. Not sure if that's just because this particular month had an extra Tuesday relative to the rest of the days of the week. But you can see that that's a pretty distinctive usage pattern. We can do this for different clusters. So here we have mobile phones. And you can see in the case of mobile phones, this access pattern looks completely different. People tend to use their Apple phones later in the day rather than early in the morning. This is outside the U.S., people looking at government websites. Inside the U.S., you see people using their iPhone throughout the day, but definitely much later into the day than they did their PCs. And if you're looking at Android users, they tend to look pretty similar to the iPhones, but they're sort of more heavy and later in the day. Useful insight into how these users are different, and perhaps into how you should optimize serving your web page if you're recognizing your people are coming in during the day versus people coming in later at night. We can also ask what types of sites do each of these user types visit. You can see here I've changed the order of the clusters a little bit to get everybody in the U.S. up here, everybody in the U.S., or I'm sorry, everybody with PCs up here, everybody on mobile devices down here. We've got U.S. people here and non-U.S. people here. You can see during January of 2012, there were a lot of visits to NASA. Just about every one of these clusters had NASA in the top 1 or 2 entries. We also, in the United States, had some people going to the New York State Department of Transportation and to this little town in Massachusetts, Shrewsbury, Massachusetts. And we can ask, where did the users come from? What's the referring website? So you can see for people in the U.S. who are on PCs, mostly they navigate there directly. You can see for people on Macs, they mostly come from Twitter. You can see outside the U.S., people mostly also come from Twitter. This is t.co. And there are some people coming in from Facebook. That's interesting. We've got redirect traffic coming to these bit.ly sites. The big question that popped up in my mind seeing all this data is what was it that happened out in space that had the Twitter sphere abuzz in January 2012? We saw especially non-U.S. users were coming to nasa.gov and to earthobservatory.com, and they were coming from Twitter. And so I did a little bit of browsing, and it turns out that in January of 2012, there were some massive solar flares. There were some great pictures on Earth Observatory, and so this explains what's driving the traffic, and it gives us some insight into what the users are interested in. So to summarize what I've talked about today, I've shown you how you can take weblog data, pull out user information by doing parsing, cluster this information into groups using Spark by applying K-modes clustering, and deliver a targeted message to each of those groups. The key points are that parsing user agent string or other data processing operations can be trivially distributed using Spark Map, that we can do clustering on large data sets with Spark, and that this clustering gives us insight into who the users are, how they behave, and we can help understand what's bringing users to our site, why are they looking at our site, when are they looking at our site, and where are they coming from. And this can all help customers to appropriately message their customers or gain additional insight into their customers. So with that, I'll just end showing the two links. The one is where these slides are available. The other is where the distributed K-modes algorithm is available on GitHub. And I'll wrap up with that.